let me just bring up this dump truck example here, and we'll talk about some of the requirements for setting up a coupling from DEM to FEA, and also some of the other quantities that we can work with in DEM. So number one, whenever we are interested in post-processing any sort of information that is related to the geometries or the boundaries, so things like contact forces against walls, impact velocities against geometries, and so on, the only way that we can gain access to those properties is by switching on a particular module. And so you'll see here in the data tree, there is a modules tab. What we'll need to do is make sure the boundary collision statistics module is switched on. Now, what this does is essentially exactly as the name suggests. So it will be recording or saving data that will be related to all collisions with particles and boundaries. Now, once we have enabled this module, you'll see it will pop up underneath the modules or activated modules list. And what you'll need to do from here is select the boundary collision statistics module and make sure that the various quantities that you'll be interested in post-processing have been switched on. So obviously, if we wanted to analyze the contact loads, we'll need to have forces for FE analysis switched on. Now, with this switched on, we will be able to export the loads into CSV files to be read into an external FEA package. And you can switch on all of the other quantities as needed. Now, important thing to note, for boundary collision statistics, the scoping of data is to boundary triangles or cells. So essentially, all geometries will have a surface mesh on them, which will be a triangular surface mesh. And essentially, any value that is displayed on that mesh or on those boundary cells or triangles is actually representative of data from all collisions which occur on that cell face. So if we take any arbitrary triangle, for example, for all collisions which occurred on that triangle face, the contact forces are actually split evenly to the nodes of each triangle. Now, this is not going to affect the total or the resultant force, but it will affect the loading distribution over the surface. And this obviously becomes significant, especially if we're coupling to FEA. Now, as a result, also, the resolution and the quality of that surface mesh becomes important. So element size or triangle size will correspond to how much information will be smoothed or averaged out. And you'll want to avoid highly skewed meshes, as that will, of course, directly skew results or the load mapping onto the geometry. So the recommended triangle size in these cases, as a general guideline, is to have them as no smaller than the smallest particle size in the model. Now we can view the surface mesh in Rocky. If I just switch off the particles view and I take my geometry of interest, which is going to be this tray, in the coloring tab, you'll see that I'll have an option to switch on the edges view. So if I check that box, you'll see it'll take a second to render, and we can zoom in and view the surface mesh on our geometry. Now, this project has already been sold, and you'll see that I'm able to plot any sort of property over that surface. So we can take, for example, the instantaneous shear intensity. So it'll take a second to render that. We can always change the contour legend. So at the moment, the max is 500. So essentially everything is red in this case. So I mentioned that we can create cumulative properties, and we showed on screen how that can be done. But effectively what we'll need to do is create a new custom property. And so I'll just create one, and let's call this example cumulative property. And let's just really quickly take the shear intensity. So this expression is, well, the field is essentially a Pythonic interface. So we have access to the information, intensity shear, through a variable A. Now I want to create a summation of the values in A, and we can essentially use Python slicing to take all of the values in A up to the current time index. So we'll put in t+1. Hitting OK will have created that cumulative property. Now, the way that we can export loads through a Rocky standalone project is super straightforward. If I right-click over my geometry of interest, you'll see an export option here where I can select to export wall loads. So I'll go ahead and do that. And what we can do is select the walls of our interest. I'll leave that to tray. Select our time domain. Let's leave this to specific time and I'll hit OK. I'll just save this here. Load data 8.2 seconds. So this will have saved a CSV file of essentially of all of the nodal XYZ locations, as well as the pressure components. So just opening that up here. And we can use this as an input for a finite element analysis. Now, the tricky part when you're working with a Rocky standalone project is how can we actually import that data into Ansys Mechanical? So I've just brought up Workbench really quickly, and essentially we can do that through this external data object here. So I've just dragged and dropped this component system from the list here. So I'm looking for an external data object, and I'm just going to double click on the setup. Effectively here, what I can do is point to a file location. I'm going to go ahead and do that. And I'm going to locate my CSV file, which contains the load data that I exported. And effectively here, we can see a little preview of our file. I'm going to need to do two things. I'm going to change the delimiter type to a semicolon, so we can see there are now 6 individual columns. I'm going to start the import at line 2 because I don't need that text, just need the numbers. And I'll need to point the columns to a data type. So I know A, B, and C correspond to the X, Y, and Z coordinates. And D, E, and F are pressure components. So PX, PY, and PZ. If I right click on that, hit update, and drag that cell into the setup cell, and just open up Mechanical, you'll see that there is an imported loads object. So in the meantime, while this opens up, you might be wondering how the load mapping actually works, given that we have geometry physically moving in Rocky, but in a finite element analysis, various degrees of freedom will be constrained at the boundaries. So when loads are exported, and I'll come back to the slides here, when loads are actually exported, they are collected in the local reference frame of the respective geometries. Now, what this means is that effectively it's the load application point that moves through time rather than the geometry itself. So we can see here in Rocky, P1 is moving, but in Ansys Mechanical, P1 stays fixed relative to our reference frame, but the load application point has actually changed instead. So I'm just going to update that in the background here. And you'll see an imported load object here where we can insert a new pressure. And effectively, this is how we can point to our DEM loads.